Hey everyone, I'm Jillian Tan, and I used to be a grad student at Michigan working under Professor Ron Jaslinski. And this was one of the things I did while I was there. And today I'll be going over teaching out of order processor design with the RISC-V ISA. So for the next 10 to 15 minutes, I'll be talking about mainly three things. And these are the three things that I hope you get. If you get nothing else from this talk, I hope that you at least get these things. The first is what we teach in this class, which is about modern CPU design. And the second is about what we make students do in this class. And they will design a RISC-V out of order core in this class. And last is, why do we use RISC-V in a class like this? What benefit does it bring? And it brings us new tools and better understanding for us. So moving on to the actual class itself, this is a graduate level architecture class that focuses on out of order and other modern CPU design techniques. And students get to form groups to design their out of order CPU by the end of the semester. And usually seniors and some juniors take this as a capstone course. Grad students who are into computer architecture or system also take this class. We see a good representation from all majors in EECS. And typically we have about 50 to 80 students with one faculty lecturer and 2 to 3 TAs. So within the class, we start in the first half by reviewing some in-order pipeline basics, quickly moving on to Thomas Sulu's algorithm, scheduling algorithm to introduce out-of-order execution. Then study some modern case studies like the P6, the Intel P6 and MIPS R10K microarchitecture. Then we move on to more things within the core like branch predictors, snapshotting, like early branch recovery, and little store queue. Moving on to the second half, we talk more about the uncore stuff like memory and caches, prefetching for data and instruction caches, virtual memory, multi-core and multi-threading for for more modern workloads, and end with a special sprinkle of the instructor's special flavor. And we have 7 labs in this class, teaching people essential skills such as writing system verilogs and using EDA tools for simulation and designing. We go over version control and basic scripting to make sure that people are better at using Linux. We go over, most importantly, we go over the RISC-V ISA that we'll be using later in this class. We got homework and exams, 3 individual projects, first 2 of which gets people familiar in writing system Verilog, the last of which gets people on board with the RISC-V ISA. Then we have the final group project, which takes up more than half the semester. For the final project, which is the biggest highlight of this class, by the way, we'll have students develop a 32-bit RISC-V out-of-order core. The class previously used Alpha 64 instead of RISC-V, but that has gotten quite a bit of age, so we updated everything to use RISC-V, and we'll talk more about the benefits of that. The design will be written in System Verilog and has to be synthesizable. Students will work in groups of 4 to 5 over 8 weeks with 3 milestones. Milestone 1 ends after 2 weeks, in which students will write their first module and test it. Then spend the next 3 weeks to complete the out-of-order pipeline for milestone 2. In week 6 to 7, they'll work on caches and memory system with an optional milestone meeting, and eventually finish integration and debugging by week 8. We provide students with the in-order processor as a starter code. In fact, they already need to modify it as one of their individual projects. They can reuse anything from it, notably the decoder, and they'll use it to verify their own design. Students will still write almost all parts of the out-of-order pipeline and integrate them. Their CPU needs to support RB32IM without the system calls and a couple instructions that we have special uses for, and they will add advanced features, which we'll talk about next, to improve performance. Their design needs to correctly execute programs, and they're evaluated on performance against their peers. These are some of the common features that students implement in their project. Many of these aren't hard to do, but offer pretty good performance gains, in return. and especially for features like the associative cache and simple stride prefetching for instruction cache. And something cool about the cache space is just that there are a lot of things that you can do within that space, so you can be pretty creative about it. And there are other features such as, slightly better branch predictors, such as Gshare, that usually give limited returns, but are pretty easy to do and slap on. One feature that almost every single group do is superscalar pipeline, usually 2 or 3 ways, which offers substantial performance boost and is what people's top priority is. We also have complex features that are kind of high return, high risk, high reward, like early branch recovery, which gives pretty good gains, but at the same time, it's hard to do. So it's a little bit less popular. And after the common features, we have some niche features. We have multi-core and simultaneous multi-threading for multi-threaded workloads. For multi-core, students usually have to come up with a simple one-way out-of-order core quickly, and then figure out cache coherence as well as load store and store conditional. This may take several weeks depending on the student's background. Likewise, for SMT, students have to have at least a two-way superscalar pipeline and then figure out how to dynamically allocate resources within the pipeline for the 2 threads. These are the things that they have to plan from the get-go, but the problem with that is we don't really teach these until the end of the semester. And to solve this problem, usually we briefly, teach students these things and work closely with the groups to make sure that they're on good track and know what they're doing for the most part. We also support exception handling, which we use to emulate certain instructions like divide, which are harder to do in hardware with unless you do it with a finite state machine. And for these, students will have to implement system calls and control registers. And we give them the trap handler as well as the functions for emulating instructions. These features are very interesting, but they don't really offer any performance gains that can be seen within our testing infrastructure, or in the case of exception handling, any gain at all. So what we normally do to compensate is we give them a flat percentage boost in performance, which translates to more points to compensate. But even then, because of how hard these features are, they have to give up other features to make these work. And the opportunity cost that's wraps up in the end just makes it not worth for most people. And the other major problem with these is just that these cannot be decoupled easily because they're so integrated within the pipeline. Unlike something like a branch predictor, if it doesn't work, you just scrap it, right, and not use it. And the reason we still offer these features and why students still do these occasionally is that these are more relevant to modern CPU designs and a very useful experience to have. These features make the processor more complete. And moving on to RISC-V, we like to use RISC-V for several reasons. The obvious ones are that it's open source and gaining industry traction, so that it's more likely that it's useful for the students in the long run. It is simple and minimalistic, which makes teaching it a bit easier. We can quickly brief students with these, and they can quickly get on board with it. But the key thing here isn't what ISA to teach, in my opinion. High performance CPU designs can be implemented on any ISA. And picking which ISA over the other for a class about high performance CPU designs isn't really that important. The ISA really complements the class and is not the focus of the class itself. We don't really teach RISC-V that excessively. We more or less just use it. What really makes RISC-V shine is its excellent software support that can enable us to do certain things that we can use to tie together software and hardware, which will get students to have a much better understanding of the computing stack. And I'll show you what that means. A really cool aspect of this class is that students get to run a lot of programs, including the ones they write, on the CPU that they designed. Test programs are compiled using GCC into RISC-V binaries. Since RISC-V supports the full GNU toolchain, we also get to use the binary utilities for debugging. As you can see on the right, there's the assembly of a compiled quicksort function. As a student, they get to see how a program is written compiled, and executed on hardware, which covers basically the full stacks of computing. To do this, we had to create a custom linker and runtime to ensure proper memory placement and initialization. We also provide a custom malloc and free for memory allocation. But all of this is possible thanks to the modular nature of RISC-V, such that you can compile programs only using a subset. RV32IM, the extensions that we use, support almost all C libraries, which means we can compile and run any arbitrary programs, which means that with a permutation of 40 instructions, you can create almost any piece of software. To test their design, students will have unit tests for each of their modules as required in the first milestone. Once they have a pipeline, then they can run assembly and C programs. Note that before the RISC-V update, we only supported handwritten assembly since there are no alpha compilers that can compile only using the subset of instructions that we picked out for the class. There are 35 plus test cases. Since we include student submitted test cases every semester, within this suite, we have some basic ones that just to see if anything works, and some corner cases to test functionalities, some common data structures and algorithms such as quicksort to reflect real workloads, and some very large programs like matrix multiplications that represent complex things like machine learning workloads to measure performance. Most of the latter two types of programs are only possible thanks to RISC-V once again. We can also generate different versions of the same test program by changing the optimization level. There are both public and private test cases. A good example of a private test case is actually, a program assignment from another class. At the end of the semester, student will turn in a verified out-of-order core that can run basically any program, as long as it can be compiled into RV32IM using our platform. It will take them to write about 4,000 lines of system Verilog code to design the core. Their design also needs to be synthesized such that it can be built into actual hardware. They can also turn in an optional test case that we can include in the test suite. Students will analyze their performance and evaluate the impact of the features they added. We, the instructors, on the other hand, will grade them based on correctness and performance measured by runtime. So in the end, I just want to summarize the things that we covered. So first, we talked about a class that we teach modern computer architecture in, and how we created a project for students to design a RISC-V out-of-order core. And we also talk about the benefits that RISC-V brings, which is the amazing tools that can be used to facilitate a processor design, especially in the educational setting. We also open source our project, so if you would like to check it out, the final project and other class materials, so if you'd like to check it out, please check out this GitHub link right here. And we want to thank everyone who helped us along the way, notably Austin, who beta tested the new projects, Sing and Shuyoung, who TA'd the class after the course change, John and Will, who developed many of the materials for the class over the years, Tom, Mark, and other lecturers who taught the class over the years, the workshop organizers for their valuable feedback and comments, and just including us in the workshop in the first place. And last but not least, the students who participated in class, without whom this would not be possible. And at the very end, I want to thank all of you for your time and patience. Thank you.